Hello, everybody. My name is Michael Brichta. I'm from Unlock Devices. I'm system applications engineer looking after industrial communications in Unlock Devices. So as we all know, industry is driven to collect more data from the sensors at the edge of any instrumentation, any process, any factory, collect more data and use those data to improve efficiency of any of the process, any factory. And for getting more of these data, of course, communications is the key to unlock the data and allow seamless communications from the edge up to wherever the communications, wherever the data information needs to get to. It's process control kind of layer or information layer or above some cloud processing, making analysis of the data. So again, communication is key to get the data from the sensors to the level above. So we are going to talk about kind of how does the connectivity architectures look like in process control, factory automation, and then we look at the edge devices and how different communications technologies, how different physical layers, what do they mean, and implication for the architecture inside the instruments. And we look from the perspective of, again, architecture, power, safety, security, and we'll see how does it lead into better communications in the whole industrial systems. So we'll start with this one, connectivity. On the left-hand side, you see the connectivity in the factory. How does it look like in many places still? It's PLC DCS with unlock inputs, output cards, and each of the unlock input output is connected to some digital sensor, switch, or unlock sensor. And where we are heading towards is more kind of TSN, Ethernet connected devices, and that will be either some software configurable input-output that connects to the sensors that still need to be connected, 4 to 20 milliamps and other means, or we can look at the IO-Link master and use IO-Link as connectivity to the edge. Then if we look at the process control, similarly today you see a lot of sensors connected through the field junction boxes and marshalling cabinets up to the I/O cards, again in DCS system. And while physically connection is very simple, it's a wire from each of the sensor through these multi-wire, multi-core cables to the PLC. The challenge comes with a scale. A typical factory would have hundreds, thousands of these nodes. I'm coming from a semiconductor company. If I look in our own factory, there are cabinets, and the cabinets are kind of that size of marshalling cabinets with hundreds of cable landing in them. So while the electrical connections are very simple, the challenge comes with maintenance, installing maintenance, replacing equipment, with the amount of sensor, with the amount of cabling, that's a challenge that the industry is facing. And also to identify which sensor is connected where and is the connection correct, and not even talking about getting more data from the sensors up to the cloud, because you have, in the way, you have the PLC. If we add hard, it's still a gateway between hard. So it's working, and there are many places in the industry that will keep working for next 5, 10, 15 years. But really, this is the future, connecting seamlessly from the sensors up to the cloud. And you can see that the topology of the connections is much, much simpler, much leaner. We have Ethernet connection to some power switch, and then they call it trunk in APL terminology, trunk connecting individual field switches, and then spurs connecting to the devices. The advantage of that, you get IP address for each of the device, and you can run control data between your controller and the individual sensors or actuators, but in parallel on the same cable and at the same time, you can get more data from the sensors and process them somewhere up to use them for optimization of the process that we are controlling. Now, let's have a look. You know, digital output device, it could be a switch. It's a very, very simple switch. Switch it on, off, and it could be some push button or some switch closing, when you're closing the door, dead end switch on end of some rail. Very simple. How can we compete with this new technology with the switch? But then we look at the switch, and how do we know that the switch actually works? That it's not on a short on a cable, accidental short on the cable, or cable got disconnected from the node. And suddenly, if you want to make the switch more reliable and add some diagnostics, it can be very simple. You add a couple of resistors, and that's a well-known technique. You get some current when it's open, still flowing. You get more current flowing that the switch is closed. And still, you can distinguish between the position of the switch and the fault conditions. But now, the digital input on the PLC now needs to get much more functionality. It needs to distinguish between at least 4 levels of signal coming from the switch. So we say simple switch, but it becomes very quickly more complicated, mainly on this side, if you want to make it more kind of reliable at diagnostics. And then we have lots of sensors in the industry that go, proximity, inductive, capacitive proximity sensors, light curtains, temperature limiters, and so on. So again, it looks very simple device, but we see more and more devices that actually would include some A to D converter, would include some microcontroller. And now you can start talking about measurement and communication. And once we get to that stage, and we put in comparison, one more 4 to 20 milliamp device, typical 4 to 20 milliamp device, you would not see many now doing complete analog processing from the sensor to the 4 to 20 milliamp loop. You will almost always find some small microcontroller in 4 to 20 milliamp device. So 4 to 20 milliamp, for somebody who doesn't know, it's 4 milliamps means 0 of pressure or temperature, whatever it is. 20 milliamps is full scale. Somewhere in the middle, any value in between is the value of the signal itself or of the measured value itself. And then there is built-in diagnostics. If it's less than 4 milliamps or cable disconnected, it's fault. If it's more than 20, cable shorted, is fault. So the diagnostics is there. And now we compare with IO-Link device, and you can see from the diagram, it's not that much different. It's the same sensor, front end for the sensor, microcontroller. Okay, you may need a little bit more on the microcontroller to run the IO-Link stack, but slave IO-Link stack is very simple, very small, and suddenly you get a device that has bidirectional communication, and it can communicate not only open-close on one value of the sensor, but you can get more kind of diagnostics. You can ask the sensor who you are. Is the right sensor connected to the right port? And you can get much more information from the sensor itself, and it leans towards better topology of the communication. Now, 4 to 20 milliamp hard instrument, more looking at the process control. In process control, you will often find similar device. Now, specific in the process control, there is much more often device need to go to explosive environment, and we'll talk about it a little bit later. So you would find intrinsic barriers. You would see maybe 2 microcontrollers because of functional safety. The information is still 4 to 20 milliamp. If we allow hard, we have to limit the bandwidth of 4 to 20 milliamp loop to 25 hertz, which is slow communication. Hard protocol has been, and there are many hard devices in the field, has been put there to put some communication, more communication between the sensor and the system, so you can get just hello, who you are, I am pressure sensor, and are you going well, are you calibrated? But the speed of hard is very slow, and again, you need a gateway between the hard and any upper layer communication. So compared to the 10BASE-T1L device, again, if you look at the diagram, it looks very similar to the hard device. It's the same analog front end, same microcontrollers, and the microcontroller size need to go a little bit up in terms of the memory, and that depends on what protocol needs to be communicated. If we stick with hard IP, it can be quite small. Of course, if you go Profinet, then you need a little bit more memory for Profinet. Again, trading off a little bit bigger microcontroller for that connectivity all the way up to the cloud. Now, we can look at the 4 to 20 mm device from the power point of view. So from the power point of view, if you look how much power is needed from a port or channel or power supply that supplies the system, how much power we need for 4 to 20 mm channel, it's about half a watt. Because we need to be supplied 20 milliamps at 24 volts. It's 480 plus some headroom, about half a watt of power that is needed for the instrument at its maximum value. And we can't predict which value the instrument is going to measure. But then we also need to supply the same instrument under condition of 4 milliamps. And you can see that it's quite little left for the sensor itself. And we can go through calculation, but it would be about 25 milliwatts. That's what's left for the instrumentation, for the measurement itself. Now, if we compare that with the APL device, the APL device is getting about the same power from the APL port, but because it doesn't need to change, it doesn't need to scale all the way down to 4 milliamps, the power available for the sensor technology itself is about 10 times more, about quarter of watt. So what that means that you still have enough power left for the communication, being in Profinet, but you have much more power left also for the instrument itself, and you can transfer some instruments that previously were not capable of running in that two-wire communication, were not be able to be loop powered. Now, for the same two-wire communication, you can get much more variety of the sensors, and you can put more sensors, transfer them to two-wire connection. So that's one advantage of moving to that technology. And then, just for comparison and for completeness, IO-Link, there is a lot of power available for the IO-Link device. You can connect solenoid sensor and power it from the IO-Link port. The challenge in the IO-Link is different. It's actually keep the power low in a very small physical sensor, because if the sensor is physically small, you need to be able to dissipate heat that you spent in the sensor. So what is important, the IO-Link, for the small sensor, that the IO-Link transmitter and the microcontroller and the sensor itself is kept a reasonably low power, that it doesn't overheat itself. Then we can look at functional safety. If anybody of you design for functional safety, you know that you need to design per the 61508 standard. You have to have design flow in place. All the check boxes take through the design cycle up to the manufacturing. So, but if you look specifically at 4 to 20 milliamps, it's a little bit tricky, because 4 to 20 milliamps is an analog channel, which means that if you get any value between 4 and 20 milliamps accidentally, the other side may consider it a valid value of pressure that is measured. So if you want to have functional safety communication over 4 to 20 milliamps, you have to actually add a lot of diagnostics on the driver of the 4 to 20 milliamp loop. So that means you have to apply diagnostics on the complete driver of the analog signal that is going out, which means probably additional ADC. You have to have a second sensor just in case the first one fails. And the same applies for the analog input sitting on the other side. And if you drive an actuator, it would flip, but still the analog channel has to have a lot of diagnostics to make sure that the value that you think you communicate to loop is actually the current that is flowing through the loop. So comparing that to the APL device, the communication itself, the link itself, is a black channel. You either do get data in time or you don't. There's no in between. And then the safety is implemented in the protocol above. Whatever that protocol is, like you can use in Profinet, you would use ProfiSafe, and ProfiSafe would make sure that the data that are communicated from your front end gets to the other side. But from the link perspective, it's actually much simpler than 4 to 20 milliamp, if you think about that. For completeness, IO-Link, and there is IO-Link safety, it's also black channel on the IO-Link. Same concept. Now, explosive safety. Explosive safety is quite tricky, but there are many people who have resolved it for 4 to 20 milliamps. You add your protection, you limit the charge or energy that you can get inside the instrument. You limit the heat that you can get so you don't get more than allowed surface temperature for the given environment. So that has already been in place for 4 to 20 milliamp. And if we compare to the APL device, it's more or less the same. There are techniques how to clamp the power coupling inductors. And for that reason that you need those clampings is the 1 volt peak-to-peak amplitude on the APL spurs. It's not the energy of the signal itself, it's the clamping. You have to be able to dissipate under fault condition a little bit higher power. But again, there are precedents for that from the field bus. There are solutions out there. So it's not that different. The principles are the same. They are well known in the industry. And you can design an APL device for intrinsic safety. Security, not really a topic for 4 to 20 milliamp devices. That's something that we need to look at if we do the APL device, because if you have IP addressability from the cloud down to the sensor, you have to be able to say, is the sensor what it is? Is it running the firmware that we think it's running? Is it the right sensor? So authentication and sometimes maybe encryption. But again, it's not that difficult, and you'll find chips that do the secure authentication, helps you with secure boot. A little bit overhead, but not much, and it's not making the device overly complex. So what we spoke about here is the industry is driving the need for optimizing the processes and factories, is driving the need for more communication, more data. The new communications technology allow better network topologies, allow you communicate more data in both directions between the sensors and actuators in the factory, and the same even more in the process. So the new technologies do allow better optimization, and they are not that much more complex. They are not as much more complex as you may have thought. So the on-off 4 to 20 milliamp loops transition to IO-Link and APL is happening. It is a little bit of challenge, but the challenge can be overcome. It's not as complex as it may seem. And it brings the seamless connectivity. It brings a lot of benefits to the whole plant manager, that he can see better what's going on in his system. Thank you very much.